Welcome to my talk. My name is Mohammad Ahmadi, and I would like to talk about distributed maximum matching problem in the CONGEST model. This is a joint work with my advisor, Fabian Kuhn. The maximum matching problem asks for an independent set of edges in a given graph with maximum cardinality, the set of edges that do not share any endpoints and has maximum possible size, like the set of red edges in this graph. We study this problem in the CONGEST model. There's a computer network that is abstracted as a graph, where the nodes represent the computers, and each edge represents the possibility of communication between two computers in the network. From now on, when I say node V, I actually mean the computer represented by node V. The communication is synchronous. That is, time is synchronously seen by all the nodes as a sequence of rounds. In each round R, that starts at time r-1 and ends at time r, every node first performs an arbitrary local computation, and then it exchanges a log of n-bit message with each of its neighbors. This problem has been extensively studied in the CONGEST model. To compute a maximal matching, which is a half approximation solution, one can deterministically solve the problem in time O of log squared delta times log of n. One can also reduce the dependency of the time complexity on n with the cost of higher dependency on delta, and solve the problem in time delta plus log star n. Using randomness, we can be faster and solve the problem in time O of log delta plus some poly log of n. We can improve the approximation ratio to 1 minus epsilon with only log delta over log delta rounds with a dependency factor on epsilon, which is polynomial in bipartite graphs, but exponential in general graphs. To compute an exact solution for the maximum matching problem, there are deterministic algorithms with time linear in the size of the maximum matching in bipartite graphs and quadratic in general graphs. So the challenging question here is whether we can do better than quadratic for general graphs. Our contribution in this work is not to actually compute a maximum matching, rather to evaluate a given matching in general graphs. More precisely, given an arbitrary undirected graph G and an unweighted matching M, we provide a distributed randomized algorithm to either verify that the given matching is maximum in O of M rounds or disprove it to be maximum in O of D plus L rounds, where D is the diameter of the network and L is the length of the shortest augmenting path in the network. An augmenting path is a path that connects two unmatched nodes, also known as free nodes, such that the edges along the path alternate between the edges inside and outside the matching. The solid edges in this figure depict the matching edges, and the dashed edges are unmatched edges, also known as free edges. The general outline of our algorithm to verify a matching is quite simple. For an exponentially increasing parameter r, the algorithm looks for an augmenting path of length at most r. To have a termination condition, it first computes the size of the given matching, and then it terminates as soon as it finds an augmenting path, or parameter r becomes larger than 4 times the size of the matching. The conclusion of the algorithm is based on a well-known fact that a matching is maximum if and only if there's no augmenting path in the graph with respect to that matching. Therefore, if the algorithm finds an augmenting path, the matching is not maximum, and otherwise, the given matching is an optimal solution. Computing the size of the given matching as the first step of the algorithm can be done in time in the order of the diameter of the network. To do so, the algorithm can construct a tree rooted at the maximum ID node, and then, by performing a converge cast over the constructed rooted tree, the total number of matching edges can be counted. Therefore, the total time complexity of the algorithm actually depends on how fast the algorithm can look for an augmenting path of some specific length. To that end, we present a randomized protocol to detect whether there exists an augmenting path of length at most r in O of r rounds of the CONGEST model with high probability. then if we have such tools at hand, the algorithm that I just described has the total time complexity of O of d plus L. O of d is needed for the first step of the algorithm, as we discussed, and O of L is the time needed for all the repetitions of the loop, where L is the last value of parameter r in the loop, which means that L is the maximum length of an augmenting path that the algorithm looks for. Now let us talk about a randomized protocol to detect the existence of an augmenting path. Consider the following protocol. We run BFS starting from all unmatched nodes in parallel. What we hope for is that over an augmenting path, two different BFS meet each other over the middle edge of the path, and the path gets detected by the two endpoints of the middle edge. One way to implement this idea is by running a simple token dissemination algorithm where tokens are the free node IDs. This token dissemination is as follows. In the first round, every free node sends its own ID to all its neighbors and then goes to sleep. After that, every node that receives some free node ID for the first time, if it receives the ID over its matched edge, it will immediately forward it over its free edges. And if it receives it over its free edges, it picks an arbitrary one, the red one here, and immediately forward it in the next round. After forwarding a token for the first time, each node also goes to sleep. The important point to notice here is that every node participates in the token dissemination by forwarding a token in at most one round, and hence a free node ID only traverses a path but not a walk containing cycles. Therefore, when a node receives a token in round R, the node can interpret this token receipt as the fact that there exists the shortest alternating path of length R from some free node. So every node learns the length of its shortest alternating path from a free node in this token dissemination. Implementing the parallel BFS with the explained token dissemination is appropriate for detecting an augmenting path in bipartite graphs, but not in general graphs. The reason is the validity of a property in bipartite graphs, which is not valid in general graphs. This property is called by Vijay Vazirani the BFS honesty property. The property says that, considering the shortest augmenting path P connecting two free nodes f and f prime, the subpath of P from F to any node V is also the shortest alternating path from F to V. Therefore, since every node learns the length of its shortest alternating path by performing the token dissemination that we already discussed, it actually becomes aware of the length of the corresponding subpath of P, and therefore it can cooperate in detecting the path. However, this property does not necessarily hold in general graphs. If we consider this example in general graphs, we can just add a free edge between f and v, which is not allowed to be added in bipartite graphs, since it obviously creates an odd cycle. Having such an extra edge, the subpath of p will not anymore be the shortest alternating path to v. Therefore, if node v only knows the length of its shortest alternating path, which is of length 1, it cannot cooperate to detect the augmenting path P, because it does not know the length of the corresponding subpath of P, which is of length 2. However, despite the fact that the subpath is not anymore the shortest alternating path to V, it is the shortest alternating path to V that contains V's adjacent matched edge. Hence, in general graphs, if we want to still detect an augmenting path, we need every node V to learn two things: the length of its shortest alternating path that reaches V through its adjacent matched edge, and the length of its shortest alternating path that reaches V through one of its adjacent free edges. For the ease of discussion in this talk, let us name the shorter alternating path the first shortest alternating path, and the longer one the second shortest alternating path, no matter which one contains V's adjacent matched edge and which one one of these adjacent free edges. Now the important question is that how we can implement the parallel BFS to be suitable for general graphs, in which every node learns the length of both types of its shortest alternating paths. To that end, we extend the described token dissemination by allowing every node to participate in the token dissemination in 2 rounds, rather than just 1 round. Consider an arbitrary node V. Let us assume that in the first round that node V receives a free node ID, it receives the tokens over its free edges. Then it picks an arbitrary one and forwards it over its matched edge. Node V commits to the ID it has forwarded, which is the red one here. Afterwards, in the first round that it receives the red free node ID over its matched edge, it forwards the ID over its free edges. It is important here to see that every node participates in the BFS of only one free node that it has committed to, but it can participate in 2 rounds of the protocol. Therefore, since every node receives tokens over its matched edge as well as its free edges, we hope for the nodes to learn the length of both types of their shortest alternating path. But the following example shows that the extended token dissemination does not properly work yet. Consider node W and free node F in this figure. By receiving token over its matched edge in round 4, W learns that it has a first shortest alternating path of length 4. And by receiving it over its free edges in round 9, it learns that it has a second shortest alternating path of length 9, which is not the case, as the walk contains an odd cycle. Moreover, when W forwards the token over its matched edge, it even confuses other nodes like Z about alternating path detection. The problem is that W is the tipping point of an odd cycle and receives the token that has traversed an odd cycle, but not a path. Now let us assume that node W somehow detects that it is the tipping point of an odd cycle and avoids forwarding the token further. We still have a problem. If we just add a path like the blue path in the right figure, W must forward the received token although it is the tipping point of an odd cycle. So comparing the 2 figures, the crucial observation is that although W is the tipping point of an odd cycle in the right figure, it is also contained in a larger odd cycle. But this is not the case in the left figure. So let me elaborate this observation a little bit more. Consider this odd cycle, whose tipping point W is reachable through an alternating path from a free node F. All the nodes inside the odd cycle have both types of alternating path. For example, node Z has the yellow alternating path that contains its matched edge and the blue one that contains its free edge. So if a node learns that it is contained in an odd cycle and knows the size of this odd cycle, then it can detect the length of both its shortest alternating paths. Let us now observe how a free node ID traverses an odd cycle and see how we can take advantage of it to implicitly detect an odd cycle. When an identical free node ID traverses an odd cycle, 2 identical tokens are sent over the middle edge of the odd cycle in opposite directions in the same round. When this happens, we define a unit flow to be generated over the middle edge and immediately be sent back towards the free node, such that half of the flow is sent over the left path and half of it over the right path. When node W receives the complete flow, it drops the flow and does not forward it anymore. This way, all the nodes inside the odd cycle receive a proper fraction of the flow, the tipping point of the odd cycle receives the whole flow, and the rest of the nodes receive nothing. This will be the distinguishing point for these nodes to learn whether they are contained in an odd cycle or just the tipping point of an odd cycle. An edge can be a common middle edge of more than one odd cycles, as you see in this figure. Then every node can equally split the flow and forwards it along the alternating path towards the free node. Node W here in this example receives a proper fraction of the flow which is generated over edge E. And it is actually what we expect, because node W, in addition to being the tipping point of the inner odd cycle, is actually contained in the larger odd cycle. Getting back to our example, W receives a proper fraction of the generated flow over edge E in the right figure, but the whole flow in the left figure. And this way, it can act properly because it can distinguish between the two scenarios in the right and in the left figures. In this example that we discussed, there's only one generated flow. But there might be many flows in the network, like the green and the red ones here. But we didn't forget that we are solving the problem in the CONGEST model, and therefore we cannot keep track of all flows separately, because we might have many different flows that are needed to be sent over the same edge in the same round. What we do is to aggregate all different flows and only forward the sum of their values. As in this figure, when a node receives both green and red flows, it just forwards the sum of the values. If we simply aggregate the flows by summing their values, then for example, node U here receives a complete flow despite the fact that it is not the tipping point of an odd cycle. Moreover, the nodes depicted by green color do not receive any proper fraction of a flow since U drops the whole flow. However, we can see that these nodes are inside these two odd cycles and should have received a proper fraction of a flow. There's a simple fix for this, and we should use randomness. When we would like to split a flow, we split it uniformly at random, instead of equal splitting. This way, when a node receives an integer flow, it knows that it has received a complete flow, and therefore it is the tipping point of an odd cycle. Otherwise, when it receives a non-integer flow, it knows that it has received the proper fraction of at least one flow, and therefore it is contained in at least one odd cycle. I didn't reveal all the details in these examples that I've already discussed, and it may raise a few questions, but I would like to mention the most important one here and present a solution for that. We aggregate different flows, but the question is that, do all these aggregated flows are to traverse the same alternating path? I provide a very basic counterexample to say no to this question and afterwards provide a solution for that. Consider the two nested odd cycles, the inner green odd cycle with middle edge E and the outer blue one with middle edge E prime. For the sake of correct odd cycle detection, the flow generated over E should only traverse the green odd cycle, and the flow generated over E prime should only traverse the blue cycle. Therefore, the two flows must take different paths when they reach W. The blue one should go to Z and the green one to Y. This example shows that flows do not necessarily traverse the same paths. However, as we already discussed, when node W receives the two flows, it only receives the sum of their values. Therefore, it cannot split the two flows properly and send the blue flow to Z and the green one to Y. What it can do is to split the aggregate value and send them to both Y and Z. To solve this problem, we have to find a way that nodes like W can forward all received flows in a consistent way, without harming the correct odd cycle detection. So what we do is to change the flow forwarding rule, but before giving you the new rule, let me present a definition. The parent of a node is its neighbor that sends it a token for the first time. So if in the first round that V receives a token, it receives it from its matched neighbor, then the matched neighbor is its parent. And if it receives a free node ID for the first time over its free edges, the ones that sent the token that V has committed to are its parents, which are Y and Z in this figure. So the new rule for flow forwarding is to randomly split and only forward the flow to the parents. Now we have a consistent flow forwarding and all the flows traverse the same path. And node W does not need to treat different flows differently and sends the aggregate flow only to its parent Y. But doing so, the blue flow actually traverses the inner odd cycle. But what we expect is that it traverses the outer odd cycle, as depicted in the right figure. To fix this problem, one can change the flow generation rule in a way that flow is generated over E double prime instead of edge E prime. Unfortunately, I have to skip explaining the rules that enforce this flow generation shift from E prime to E double prime. But what I want to explain here is that why generating flow over E double prime instead of E prime does not hurt the correct detection of the blue odd cycle. The flow generated over E double prime is sent by its endpoints to their parents, as depicted by orange arrows. The only nodes that differ in receiving the orange and blue flows are the ones inside the inner odd cycle. Since these nodes have already received the proper fraction of the green flow generated over edge E, receiving orange or blue flows are irrelevant to them. Therefore, we can safely generate and propagate the orange flow instead of the blue one. So we changed the flow forwarding as well as the flow generation rules so that all the flows received by a node traverse the same path later on. Let me recap here. We talked about a simple token dissemination to implement parallel BFS in bipartite graphs. We extend the token dissemination to allow every node to learn the length of both their shortest alternating paths in general graphs. To make the extended token dissemination work properly, we equipped it with a flow circulation protocol. The combination of the extended token dissemination and the flow circulation protocol allows every node to commit to a single free node and also learns the length of its first and its second shortest alternating paths. The fact that every node only commits to a single free node creates a disjoint clustering over the nodes, which we call the free node clustering. It can be shown that there exists an augmenting path that is partitioned into exactly two pieces, such that each piece is completely contained in one cluster. Since the two nodes U and W at the border know the length of their shortest alternating path that contains their adjacent matched edges in this figure, they can compute the length of the augmenting path on which they reside. Therefore, the augmenting path can be detected by the two nodes at the border. It is important to mention that although this clustering allows to detect an augmenting path of a specific length, it cannot construct the path efficiently. If we could actually construct the path, say in time linear in the length of the path, then we could, similarly to the algorithm for bipartite graphs, compute the exact solution for the maximum matching problem, also in general graphs in almost linear time. At the end, I would like to mention something as the potential next step of this work in the future. If we consider the clustering that we already discussed, there is no guarantee that the detected path is partitioned into two neighboring clusters in a well-balanced way. And the partitioning could actually be completely unbalanced, like in this figure. The interesting question here is that, can we modify the clustering algorithm such that we can make sure that there's an augmenting path that is partitioned into two clusters with a well-balanced partitioning? If we could guarantee that, then by repeating the same clustering within each cluster, we could actually construct the path with the cost of an extra logarithmic factor. I would like to thank you for your time and listening to my talk.